Sorry.
I'll probably come to the...
Okay. Okay, well, hi, everyone. Let's get started. First of all, if you're one of the speakers and you haven't sent your slides, well, to the email address that was just shown, please do that as soon as possible. This will be a session on LLMs, an official entry of call to the LLM era. Our first session, our first speaker, once he has the slides, will be Nirmit, and he will talk about the a theory of learning with autoregressive chain of thought.
Thanks. So this is joint work with a lot of great people. So our goal is to understand this paradigm of learning with autoregressive chain of thought. So which is, when you ask model a question, it generates a sequence of tokens first, which is chain of thought, and then it arrives at the final answer. So formally what you have is a sequence to next token generator, which is a mapping from sigma star to sigma, which you can think of as your transformer. And you define this output append operation, which is you just generate the next token and append it. And then you can apply this function multiple times, t times, to generate a chain of thought, which is a sequence. And you take its last bit as the output. You take the last token as the output, which I'm going to call end-to-end mapping. And now for a class of sequence to next token predictors, you can think of a hypothesis class of end-to-end mappings, which are all possible end-to-end mappings. One thing I would like to emphasize here is that this autoregressive process here is time invariant. In particular, what I'm doing is I'm taking the same function, the transformer with same set of parameter multiple times to generate the entire chain of thought. And this is going to be a very important distinction from Malak's work for those who are familiar with this. Okay, so our goal is to, we are in the distribution-free realizable learning setting. So you have some distribution which is unknown, and you are going to get samples from it IID. And for some ground truth F star, I'm going to consider two settings. So one is end-to-end learning setting, where you only observe the question and the final answer without observing the chain of thought. And the second setup I have is the COT learning setting, where I also get to observe this chain of thought. And in either cases, our goal is to minimize end-to-end disagreement error, which is the 0-1 loss of my learning rule, that it disagrees on the final output. And the question we ask is that, in terms of the properties of the base class and my generation length t, what is the complexity of learning this end-to-end mapping in either of these two settings, and how these two settings contrast with each other? Okay, so let's first talk about the sample complexity. So if my class is bounded cardinality, so does my end-to-end class, and I get this nice log cardinality bound. So what about VC classes? So for VC classes, what I get is t times VC dimension of f, which is also tight in the worst case. And this is disappointing, because with this time invariance, my whole point was to establish the fact that I just have to learn one function despite having these t steps of composition. So this t dependence on linear in t dependence on sample complexity is in some sense disappointing. But this is still for end-to-end learning. What about COT learning? With COT, what I can get is VC dimension times log t. So this is like, I'm avoiding this t dependence in sample complexity. Now let me return to the end-to-end sample complexity and ask, like, still it feels like I just have to learn one function. So why should my sample complexity should depend on linear in t? And the question is, can you go beyond cardinality while still avoiding this dependence in t? And the answer turns out to be yes in terms of Littlestone dimension. And the reason is that despite the fact that you have to learn the same function, this autoregressive process is fundamentally sequential, and hence the batch notions like VC are not good enough. Okay, so this all is nice, but this is more like a benefit of time invariance than the benefit of chain of thought. So what is the real benefit of chain of thought is actually computational. So if you have, if you observe the chain of thought, then the goal of learning the end-to-end class just reduces to the supervised learning problem of the base class. In particular, if the base class has consistent tractable rule, then you can also learn with chain of thought for the end-to-end class. What about end-to-end learning? Which is not so this particular thing is not the case, and end-to-end learning can still become hard. So what is the most natural simple class for which we know that the base supervised learning problem is easy? The class of linear thresholds. So this class is just, you are on the Boolean hypercube, and in order to generate the next token, you just take a linear threshold and generate the next bit. So this is my class. And what I'm going to show is that end-to-end learning for this particular class is hard. And the way it is shown is by expressing the class of constant depth circuit as the end-to-end mapping of this class. In particular, what I can show is that for any circuit, any constant depth circuit, I can encode it as a linear threshold so that if I apply the same linear threshold again and again, as the end-to-end mapping, I can realize this circuit. And the size of this linear threshold would be the size to the power depth of the circuit. So one might also think of this as a learnability result. In particular, like, I know that constant depth circuits are hard to learn. So this, with chain of thought, I can maybe learn these classes, these hard classes. But from learnability point of view, this result is disappointing because the sample complexity for me to require to learn this class would be sized to the depth of the circuit, which is much larger than what I directly need to learn the circuit. So should this motivate us to try and improve on this result? And actually, the answer turns out to be no, because circuits are fundamentally non-time invariant model of computation. So what kind of universality do we even need if I don't want to learn the circuit? So let's try to decouple between two things. Let's try to decouple between the description length of a program and runtime of a program. So let me consider this class of program of size S that run in time at most t. And there are many programs with like very low description length and that can run forever. They can run for like a lot of time. It's fine if my runtime of the learning rule in order to learn this universal class depends on t. But this amazing universal class has log cardinality bound of just order S. So in order to learn this class, the sample complexity I need is just order S. And the question is that, is there any iterative natural base class so that I can express this universal class as the end-to-end mapping of that class? I can learn this class with, let's say, order S or poly S or S log t samples. I'm fine with log t dependence. And I know this, I can have this two decider data already by just doing ERM on the class itself. The question is, but the ERM over this class is intractable. But now I have something called as chain of thought. So can I learn this class in COT with just poly t samples? And the answer turns out to be yes. I can have this all three decider data simultaneously by using attention. And I would invite you to take a look at our paper for how this is possible. So just to summarize, so we have some interesting framework to capture like this autoregressive learning setting paradigm. And there are, so both like one without chain of thought and one with chain of thought, both settings are very prevalent right now in the industry. So in particular, when the COT is especially available in the supervised fine-tuning phase in the post-training, where these companies are really spending efforts and money in order to collect these data sets. COT dataset. Also, recently we have seen a lot of success with end-to-end approaches like DeepSeek, where you just do RL from the end-to-end feedback, and you can see success. And our result shows that this is not possible without making any further assumption. And one plausible hypothesis is that these pre-trained models have some kind of good coverage property, and so that these end-to-end methods can succeed on top of it, and whose evidence you are going to see in the very same session. And the pre-training phase, where this kind of magic happens, already is more like COT than end-to-end data. The other thing is sometimes you don't even need this end-to-end feedback. Sometimes you just ask it a question at the prompt time, and at the inference time, the model is able to come up with the final answer, because there is this amazing transfer learning effect that happens. And it's very interesting and we can model this transfer learning and understand this. Some interesting future study, what we can do with, let's say, large amount of end-to-end data and very few amount of COT data, because this COT supervision should be seen as very expensive. So I know that for a fact that even for most basic things, my end-to-end learning goal is hard. And I have like universality result with moderate number of samples. And the question is, where is this limit? How many minimal COT samples do I need in order to break the hardness barrier of end-to-end learning? Is like very few example enough? One example is enough? I don't know. Another interesting question is that what if I have like multiple experts that give me different chain of thought, but they both have the same final answer? Another interesting setting is, what about the agnostic setting? What is the right model of misspecification even for the chain of thought learning? In particular, you are going to see some good candidates in the next talk, and we also have a poster with Jean and Nati outside. And in particular, I also see this setting where you have multiple experts as one interesting kind of misspecification setting. So because each example will be realized by a single function in your class, the entire data may not be realizable by any single function. And that's all from my side, and I would like to take some questions if you have any.
Questions for Mérieux? If there are no questions, let's take the speaker again. So our next speaker is Dhruv, and he is going to talk about computational statistical trade-offs at the next token prediction barrier.
Thank you. So this is based on joint work with Adam Block, Audrey Wong, Akshay Krishnamurthy, and Dylan Foster, most of whom I think you have seen milling around the conference. So the motivation for this work is an empirical phenomenon known as error amplification, which has appeared in several different domains. In offline imitation learning, it's been observed that a robot trained via behavior cloning to imitate expert actions will often tend to drift to worse and worse states over time. And in autoregressive language modeling, it's been observed that a large language model trained via next token prediction and then autoregressively sampled may sometimes lose coherence as the generation length gets longer and longer. And some empirical work has posited that a source of this error amplification might be misspecification between the data and the model class that's being optimized over. And so this raises the question, can this be avoided by more sophisticated training algorithms? So in this talk, I will give a formal definition of autoregressive sequence modeling, viewed in terms of agnostic distribution learning, and I'll show how we can quantify error amplification. You can think of offline imitation learning in some sense as a generalization of sequence modeling, but in the spirit of this session, I will be focusing exclusively on sequence modeling. I'll then talk about the statistical gold standard for this problem of how we can mitigate error amplification, and the meat of the talk will be two different lenses on what you can do with more practical and more computationally efficient algorithms. And the main takeaway will be that some improvements are possible and practical, but there is a fundamental computational barrier that prevents us from entirely avoiding error amplification. So let's start with definitions. In autoregressive sequence modeling, there is some prompt space, there is some response space, which is a space of sequences of some length h. There's a model class that we're optimizing over, and there's an expert model pi star. A model is just a map from prompt to distributions over responses. And crucially, we are in a misspecified setting, so we are not assuming that pi star lies in the model class. We receive IID samples. A sample consists of a prompt and a response drawn conditionally from pi star. And our goal is to produce some estimate, some model pi hat, which is close to pi star in some notion of distributional distance. So this is squared Hellinger distance. If you're not familiar with this, you can think of total variation distance, and the main gist of the talk will be roughly the same. This is squared Hellinger distance on average over a random prompt between the conditional distributions of pi star and our estimated model. Ideally, we would like this to be extremely small. Ideally, it would go to 0 as the number of samples goes to infinity. This is not necessarily possible. It's not possible if pi star does not lie in the model class. So we're going to aim for an agnostic guarantee, where we want to compete with the best-in-class Hellinger error. And let's say that we compete up to a factor, which we call C sub APX. We call this an approximation ratio. We would like this to be as close to 1 as possible. And we'll think of this as quantifying error amplification, because if this is much larger than 1, then somehow we are incurring error that is much larger than the inherent error due to misspecification for this task and for this model class. So that's the problem, misspecified sequence modeling. How do people solve this in practice? They learn token-level conditional distributions of pi star. In particular, the cornerstone of language model pre-training, as you all know, is next token prediction with the log loss. So this is maximizing log likelihood of each token in your dataset conditioned on the previous tokens and on the prompt. As I mentioned before, this has some empirical flaws where errors tend to amplify over the horizon. And this can be theoretically corroborated by the observation that this algorithm's approximation ratio actually scales at best with the horizon. It turns out to be much worse, but at best it scales linearly in the horizon. And so the question here is, can we do better with different training algorithms? More specifically, for any sequence modeling algorithm, we can define its approximation ratio as the best factor in front of the best-in-class error that it achieves. And we can ask, what is the best approximation ratio achievable? And then what are the computational barriers, the statistical barriers, and then the practical barriers to mitigating error amplification? And that's our main question. So let's start with the information theoretic perspective. It turns out this is already solved. So a recent work from the classical statistics literature shows that there is an algorithm called the row estimator, which actually achieves approximation ratio that's order 1. There's no dependence on the horizon, no dependence on anything else. So this is the statistical gold standard. Unfortunately, it's computationally unattractive. You would not want to implement this because, for one, it involves min-max optimization over your model class. And for two, it involves these sequence-level density ratios between different models in your model class, which generically will be exponentially large or exponentially small in the horizon. So can we achieve similar guarantees by more practical algorithms? What is a practical algorithm? Well, maybe it's a modification of the algorithm that people already use, which is next token prediction with a log loss. What are the failure modes of this algorithm? It turns out there are 3 different failure modes. So the approximation ratio of log loss next token prediction it gets larger as you want to get your failure probability smaller and smaller. It also gets larger if your density ratio is bad. This is the worst case density ratio between pi star and any model in your class. So maybe pi star covers some things that models in your class do not cover, and this is a problem for this algorithm. And then the third failure mode, as I mentioned before, is that this approximation ratio linearly scales in the horizon. So what we show is the following. The first 2 failure modes are avoidable by fairly practical modifications. The first can be avoided by a boosting step. Essentially, you do cross-validation using a finite class version of the row estimator, which is efficient. The second failure mode can be avoided if you have density query access by some sort of smoothing mechanism. If you don't have density query access, this is an interesting open question. But the third failure mode, the dependence on the horizon, is actually fundamental for all next token prediction-like methods. Essentially, these are methods that, similar to next token prediction, are individually learning the conditional distributions of each layer. So the takeaway here is that you can get your approximation ratio down to be just linear in horizon with no other dependencies, with fairly practical modifications, but you cannot do better. And this is what we call the next token prediction barrier. OK. Now, you might ask, what if there are other algorithmic tools that we can employ that do not fall under this framework of next token prediction? What if there's something more clever we can do? So to try to get at this question, what we will now do is discuss a concrete model class where we can try to give upper and lower bounds for end-to-end computational efficiency. So this is the class of autoregressive linear models. Let's fix some feature map phi mapping from sequences to d-dimensional real vectors. We define a policy class in terms of this feature map, where for every policy, the conditional distribution at some particular step is a softmax it's a softmax linear function in these features. So this is essentially a simplification of real autoregressive sequence models, where we have frozen the features phi instead of having them be parametric and learnable. And what's nice theoretically about this model is that if you want to learn them well-specified autoregressive linear models, so if you receive data from an actual autoregressive linear model, this is actually end-to-end computationally tractable. There's a poly-D time algorithm for this. And this makes these models a natural testbed for understanding what is the computational price you pay when you introduce misspecification into the learning problem. The first result we show is negative. We show there's a hardness here. We show that if there were a polynomial time algorithm that can achieve approximation ratio substantially smaller than the horizon, so long as the feature dimension is large enough, then the learning parities with noise cryptographic assumption can be broken. So this seems unlikely. The interpretation here is that error amplification at a level roughly linear in horizon can be computationally fundamental even when it is statistically avoidable by the row estimator. The second result we show is that not all hope is lost. So there is a way to get a smooth trade-off between approximation ratio and runtime, at least when the number of action, or at least when the token space is size 2. So we show that for any parameter k, we can achieve approximation ratio h divided by k in time complexity exponential in k, but not exponential in h, not exponential in dimension. And so as one example, we can achieve a sublinear approximation ratio in sub-exponential time by appropriately choosing k. It's like h to the 1/3. To conclude, what we've shown is that standard algorithms for sequence modeling suffer from error amplification under misspecification, and this can be partially mitigated, but there are fundamental computational obstacles roughly at the approximation ratio being linear in horizon. Some future directions include understanding if there are broader notions of computational tractability that enable practically avoiding error amplification and achieving something closer to order 1 error amplification, order 1 approximation ratio. And also understanding maybe distribution learning is too hard of a task. Maybe there are weaker and easier goals, such as if we want to optimize some downstream generation quality with respect to some family of rewards. That's all I have. Thanks for listening.
Questions for Drew? Well, others think. Can you perhaps say why you're using the Hallinger squared distance as a kind of measure of approximation? Is there kind of a natural reason, or is that makes the techniques go?
Yeah, so I guess there's two questions here. Like, one is Hallinger versus TV. I see this as mostly technical. I would be happy with either, and Hallinger is just cleaner in some ways. The other question is Hallinger versus KL. And for that, the motivation is that KL can be infinite even when Hallinger is like quite small. So Hallinger, I think, captures these sort of like outlier robust settings better.
For the result of the row estimator, so what is the sample complexity?
It's like essentially the same as the well-specified rate. So I think it's just like log pi divided by n.
Okay.
N samples.
And the C approximation, do you know if it's possible to get exactly one, or is,
there are some prior works we cite which study these sort of fine-grained gaps, I think for total variation. And I think they show that there's like, you can get like 3 or 2, like somewhere between 2 and 3, but not down to 1. That's for total variation, but I imagine something similar is true for Hallinger.
okay, thank you.
Yeah, I have a quick question. So have you considered some kind of a smooth version of KL so that it will not happen, it will not be like infinity in the weird cases?
A smoothed version of KL.
Like if it's like forward KL, then KL pi star and pi hat, then the problem happens when pi hat is like assigning 0 probability
Yes.
to some output. But you could like define KL, add some kind of smoothing so that will not happen, right?
Right. I guess, yeah, I've not actually thought about that, but like if you add some smoothing, I would imagine that there is some sort of correspondence between Hallinger and Hallinger and the smoothed KL, where you can like bound them.
Might be some interpolation with some
But
other.
yeah, it depends how you choose that smoothing. Like if it's 1 over h or something, I don't know, there could be some interesting behavior there.
Okay,
Yeah.
thank you.
All right, let's take the rest of the questions offline and thank the speaker. Well, our next speaker is Jackson Lee, and he'll talk about generation through the lens of learning theory.
Hi, everyone. I'm talking about generation through the lens of learning theory. This is a joint work with Vinod Raman and Ambush Tawari. As we all know, there's a growing interest in generative AI recently. However, the theoretical fundamental of generative AI is kind of lacking in the literature. So what is generation AI in total? It's tons of definitions. For example, in Wikipedia, it says that the model learns the underlying pattern and the structure of the training data and use them to produce new data based on the input. Although there are different definitions, we can sort of think about the basic idea of generation is kind of simple and clear. So generation needs training data, and it produces new data. And it produces data that looks like training data. So based on these 3 basic assumptions, we formalize the generation as a sequential 2-player game between adversary and the generator. This formulation generalized the notion of a language generation in the limit from Kleinberg and Mulunasian. We also introduced 2 new paradigms of generation called uniform and non-uniform generation and provide their characterizations. We also uncover fundamental differences between prediction and generation. So as we said, we formalized the model from Kleinberg into learning theory, and through this formalization, we can uncover a lot of different new findings. So to begin, let X be an abstract countable instance space, and let H be the collection of functions that is the hypothesis class that maps the instances into a binary label. And for every edge belong to this hypothesis class, we define the support of H as all the instances such that H of X equals to 1. So for example, we can think about the instance space as all the natural numbers. And for each n, we define Hn as the support of Hn as all the multiple of n. Then, as the picture stated, we can define the hypothesis class. So the game starts that we have instance space X and the hypothesis class H. And the learner only knows H. So the game is adversary first chooses the edge star belongs to the hypothesis class and the enumeration of edge star. And at each time, it reveals xt. So the learner generates a new instance that is not observed so far. The goal is that the learner generates successfully if there's a finite sample t star such that for all t greater than t star, the generated instance it belongs to the support of edge star. Of course, we assume that the support of edge star is infinity. Okay, so for example, if the adversary picks edge 2 and reveals all the multiples of 4, although the learner cannot know that it actually picks x2, but it can successfully generate because it can always generate a multiple of 4 to win. There are actually 3 variants of the model. The first is generation in the limit. So T star can depend on S star and the enumeration. And for non-uniform generation, we define T star can depend on H star, but not on the enumeration. And finally, for uniform generation, T star only depends on the hypothesis class, but not on the single hypothesis. And generation in the limit and uniform generation are actually introduced by Kleinberg, but we introduced the notion of non-uniform generation by ourselves. And the key result is that we introduced the closure dimension, which both uniform and non-uniform generation can be characterized by closure dimension. And we also find that closure dimension is related to generation in the limit. So to begin, we suppose the learner have observed n distinct instances. Then we define the version space as all the hypotheses such that these n instances is consistent with this hypothesis. And if x belongs to support of h for every edge in the version space, then it is safe for the generator to play from it. So it is safe to play from the intersection of this version space, as we define the closure as the intersection. So in our previous example, if we observe 4, then we can see the version space is then h1, h2, and h4, and then the closure is all the multiple of 4. If we further observe 6, we can see that h4 is no longer consistent with the instances. So the closure is all the even numbers. And if we even observe 5, then the version space only contains h1, so the closure becomes to all the natural numbers. From this example, we can see that as n grows bigger, the version space shrinks and the closure expands. And once the closure is infinite, the learner can win because it can always play from this infinite set. So if we consider the smallest non-negative integer d such that for every d plus 1 distinct instances, either the version space is empty or the closure is infinite, we then call d the closure dimension of h. And if this d doesn't exist, we call the closure dimension is infinite. So one of our key results is that H is uniformly generatable. It's equivalent to say that the closure dimension of H is finite. And we observed that finite class have finite closure dimension, so we can give a corollary that any finite class is uniformly generatable, which is one of the main results from Kleinberg. We also observed that H is non-uniformly generatable. It's equivalent to say that there exists a countable sequence of HI such that H can be the increasing union of HI, such each HI has a finite closure dimension. As a corollary, any countable class is non-uniformly generatable. This is also strictly improves the Kleinberg's result, which states that any countable class is generatable in the limit. And this corollary is also independently proved by Charika and Paparaju, which will also be introduced in this session. What's more, we found that if H can be written as a finite union of different HIs, such that each HI has finite closure dimension, then H is generatable in the limit. However, we found that if we extend this finiteness to countable sequences, the theorem is not true. So we leave an open problem that what characterizes generatable in the limit. And another key result of our paper is that we study the difference between generation and prediction, and turns out they are incompatible with each other as stated in this picture. So the best evidence of this difference is their behavior on the unions. So we all know that prediction will behave on the unions. If two hypothesis classes are packed on lineables, so is their union. However, this is not true for generation. For example, we find a hypothesis class, H, which has 0 closure dimension. However, if we only add a simple hypothesis to it, it is no longer non-uniformly generatable. And there's a kind of new model, and there's a lot of follow-up work. For example, we also study the prompted generation, and there's people study validity with breath feedback, noisy examples, and representative learning. And there are a lot of future directions of this model. For example, how to generalize this into a stochastic setting, into how to incorporate this with privacy, and also how to generalize this into like a continuous instance space. We also have a main open problem of this paper is what characterizes generatable in the limit. And as a step of this open problem is the finite union of non-uniformly generatable classes generatable in the limit. It's actually already solved by Steve Hanek actually less than a month ago, and the answer is no. So there exist 2 hypothesis classes that are both non-uniformly generatable, however, their union is not generatable in the limit. And there's still a lot of open problems in this area, and that's all for my talk. Thanks for listening.
Questions for Jason? I'll have a quick question. Is there some, maybe I'm curious, how does computation enter this picture? Are there any interesting, efficient algorithms and examples of things that you could maybe generate this model that, I don't know, look like potentially useful for generating?
Yeah, this is a good question. So algorithm is also one of the future directions we are mainly concerned about. But for generation in the limits, actually for Kleinberg, if we only use the oracle, is the instance belongs to the hypothesis, we can only use that oracle to give a efficient algorithm for generatable in the limit. But for uniform and non-uniform generatable, we are still considering what oracle we should use and how to incorporate it into algorithms. Yeah.
Any examples of known examples of algorithms? I don't know. Is what it would be the equivalent of a linear classifier in this setting?
Yeah, right now is, I guess, sorry, no quick example in my mind, but we can definitely talk offline. Yeah.
Sure. Any more questions? If not, let's thank the speaker again. Crystal? Okay. Our next speaker is Crystal, right?
Yeah.
And he's going to talk about learning algorithms in the limit.
Good afternoon, everyone. My name is Hristo, and today I'll tell you a bit about our paper, Learning Algorithms in the Limit. So this paper started from a single question. Can an algorithm learn any computable function after finitely many observations? In other words, can we design a learning system that can perfectly adapt to any computable task after receiving only finitely many examples? Here, by a computable function or task, we mean any mapping which is a result of a harnessable physical process over some computation domain. So a computation domain, for example, could be the voxels of a kitchen sink. The computable mapping could be washing the dishes, and the computational process in the background could be my brain telling my muscles how to move in order to complete this mapping. Hence, the question that we're interested in is, can a robot learn how to do the dishes after observing me do it finitely many times? Now, the robot might have no prior information on the physical process that brought about F, but fortunately it doesn't need to, because of the Church-Turing thesis, which says that under a reasonable encoding, any reasonable encoding of voxels into finite strings over some finite alphabet sigma, there is a Turing machine T, which simulates exactly the computation process behind F. So if we define as C sigma star the class of all Turing computable or recursive functions over sigma star, then this class modulo and encoding contains all computable tasks. And in this talk, in order to stay light on notation, we're not going to discuss encodings anymore. We'll just consider our computation domain to be sigma star, and we'll ask the question, can we learn the class of functions C sigma star with finitely many observations? We'll answer this question in the Learning in the Limit framework that was developed by Gold in 1967. So apart from being interested in language identification from positive examples, Gold also formulated a framework for learning computable functions. In this framework, computation is done over a domain sigma star, where sigma is some finite alphabet. And there is a target function class omega, which is some subset of computable functions. Now, at each point in time, there is a learner who observes examples, input-output examples, from a ground truth function f. In this illustration, the alphabet is a set of mathematical symbols, and the computable function is finding the roots of a quadratic equation. Now, the learner has the following guarantee. He will see all of the examples at some point in time. So there is an ordering of inputs W, which is surjective, and at some point in time, all of the inputs are visible. So at time t, the learner generates a hypothesis h of t, which is based on the observed examples. And we say that L learns omega in the limit if for every f in omega and every ordering, there exists some time t star, after which the learner outputs the correct ground truth. Okay, so under this criterion, Gold proved the following negative result. The function class of all computable functions is not learnable in the limit. So no matter how much memory, computation time, or access to observation an algorithm has, learning every computable function is out of the question, which is a bleak conclusion. But in the real world, an intelligent system hardly ever learns from such impoverished input-output observations, because learning systems observe computational processes and not the mere results of computation. For example, in human learning, teachers give multiple intermediate steps between the input and the output of some mathematical problem when they explain it to the class. And machine learning research has shown that if you pre-train on chain-of-thought data, the accuracy on algorithmic tasks improves considerably. Because of these considerations, we develop a generalization of Gold's framework that puts the computational process at the forefront. And we need some notation first. So with M sigma star, we denote the family of deterministic discrete time computation models on the set of finite strings. So this could include RNNs, transformers, Turing machines, possibly human brains. With f of m, we denote the set of functions computed by the model class M. With small f of m, we denote the function computed by a model M. And with alpha mx, we denote additional information that is available as an observation of the computation process. Now, recall the framework of Gold, and we'll see step by step how we generalize this setup. First, we introduce an input restriction, because computable functions often come equipped with a natural set of inputs. For example, when students learn in school how to find the roots of a quadratic equation, they don't just observe at input any possible string of mathematical symbols, they observe valid quadratic equations. So it makes sense to restrict the possible set of strings. Then, at the forefront, we put a target model class, and we consider alpha observations, which can include additional information about the computational process. Now, the input ordering is over the restricted input. the observations take into account the additional information, and we say that the learner solves the M-alpha learning problem if for every model in the model class, every restriction of the input and every exhaustive input ordering W, there exists some time T star, after which L outputs an I equivalent representation of F. In other words, after a finite number of examples, the hypothesis will agree with the ground truth on the restricted input domain. Now, as we mentioned, this class of models M sigma star contains a variety of different model species. It could be transformers, RNNs, brains, whatever. And in order for a unified strategy that is model agnostic to exist, we rely on a relaxation of the extended Church-Turing thesis. So for a computable and monotonically increasing function Q and a model M in this set of computable models, there is a Turing machine which operates on sigma star and a constant C, such that any n steps of M can be simulated by T in at most Q, C, n steps. If Q is n to the power C, we recover the usual extended Church-Turing thesis that is used in complexity theory. Now, the first source of additional input observations that we consider is no additional information. So alpha is the empty string, and we consider this FM learning problem. This is Gold's original formulation plus the restriction of the input sources. And Gold's theorem says that no algorithm solves the C sigma star learning problem. Surprisingly, if we restrict the complexity of the target function class, we get learnability. So if we consider Qm to be the set of functions for which there is a model inside curly m, which computes the function in at most Q, C, n steps, we define as such the complexity class. So if big Q is n to the power of C, we get the polytime computable functions from the model class M. And with this notation, and assuming the relaxed extended Church-Turing thesis, we prove that there is a learning algorithm which solves this learning problem. And even if we don't use the relaxed Church-Turing thesis and we restrict our attention to Turing machines, we get for free that the popular complexity classes like P and P sharp P become learnable in the limit from restricted input sources. The next set of additional observations that we considered are time bounds. So in this setting, the learner only gets an approximate information about how hard the underlying problem is. He gets an alpha TB, which roughly upper bounds the number of steps M of x takes. And more formally, this means that there is some up to a constant alpha TB bounds the number of steps. So in order to motivate this setup, we can consider a robot that only has access to an input-output terminal, and given an input, the robot collects the number of seconds between the input and the output. And if each internal step of the algorithm takes 1/cm steps, then alpha TB satisfies this rough upper bound property. And assuming that we have access to these observations, then we can learn any computable function computed by any possible discrete time model. Again, if we don't consider the extended Church-Turing thesis, we recover the same results, but constricted to Turing machines. So in summary, we extended Gold's computational learning framework by adding computational observations and restricted input sources. We proved the learnability of parameterized complexity classes from input-output observations, thereby extending Gold's original result. And we also proved learnability of all computable functions from time-bound observations. In our paper, you'll find an additional source of additional information, which is considering all the intermediate computational steps. And there, stronger results can be proved. We also give some power efficiency arguments through characteristic sets. And if you enjoyed this learning framework and you have interest in future directions, please come and speak to me. And thank you for your time.
Questions for Hristo?
Yes, hi, great talk.
Hello.
I wanted to ask, like, what is the exact kind of number, that threshold above which the, like, computable function is learnable? Like in, like, something like sample complexity in your framework?
Yeah, so with exponential sample complexity, we can learn everything. If the ordering of examples is good, like if there is some curriculum, the ordering is not adversarial, we can also learn with even a constant number of examples, but this involves collusion. So it's very hard to not have a colluding framework and a good curriculum.
Thank you.
Thanks for the interesting talk. So it seems like you extended, you have observations and restricted input sources. I was wondering about a different axis where maybe the learner has interaction and can ask for specific examples or the ordering to be presented in a particular way. I was wondering if you had thought about that and maybe what kinds of things that could buy you.
Yeah, so this learning framework was considered by Anguin, and it's a strictly more powerful framework. So a negative result here translates to a negative result there. And in the paper, you can see that we have an argumentary characteristic sets that you need an exponential number of samples, even if you have the intermediate steps. So this translates to this setup as well. But yeah, I mean, it's a bit technical, so I'll be happy to talk with you offline about this.
All right, let's thank the speaker again. Well, our next speaker is again Dhruv, and he's going to talk about language model reinforcement learning, exploration, and the computational role of the base model.
Thank you. Yeah, this is the new title. This, I guess, is about language model reinforcement learning. So I think the organizers just flipped a coin deciding which session to put it in, and here I am. This is based on joint work with... Come on! All right, next talk. This is based on joint work with Dylan Foster and Zach Mamedi. So large language models, the pipeline consists of essentially three phases. There's pre-training, there's post-training, and there's inference time algorithms. So in pre-training, there's a huge amount of data, huge amount of compute time, and you learn a next token predictor. In post-training, you have limited compute, and you have very limited reward data, because you want it to be very high quality and more task-specific. And you're trying to do reinforcement learning to make the model, the pre-trained model, have even better performance on some tasks you care about. And then there's inference time algorithms, which I'm not going to talk about. In fact, I'll just be focusing on post-training. So I'll assume we have some base model from pre-training, and now we want to improve it. So recent empirical work has suggested that current RL methods for post-training may just be amplifying behavior that is already present in the base model. Maybe the base model solves some math problem with probability 1%, and it gets amplified to 5%. Maybe it solves with probability 5%, and gets amplified to 10%. But the question this raises is, can we get models to discover truly novel behaviors in post-training that were like exponentially unlikely, for example, in the base model? So if you're familiar with RL, you will know that this is sort of the bread and butter of theoretical reinforcement learning. We all know that reinforcement learning with active exploration can learn behaviors that would have been exponentially unlikely under the base model, because in classical RL, there is no base model. You could think of it as the uniform model, uniform policy, and yet we can still learn good behaviors. And we know that the sample complexity of active exploration can be exponentially better than these sort of greedy passive techniques. But we also know some hardness results. We know that the computational complexity is often much worse than the computational complexity of passive exploration, even in quite simple models. Seems a little cut off, but there's just a question mark on the side. So this is somehow fundamentally unsatisfying. And somehow you want your algorithms to work at least in very simple models. And it's potentially a confounder to empirics. If you want to say, does my exploration actually have value? It's maybe a confounder if you're trying to use heuristics to implement your computationally intractable algorithm. So in this talk, we're going to discuss a theoretical toy model where we can formalize these issues of statistical versus computational efficiency. And we'll see that passive exploration and active exploration both have downsides. And then we'll discuss how we can get the best of both worlds with a new algorithm. And I'll finally discuss some technical vignettes about improvements and limitations that we can see from these algorithms. So let's start with definitions. A language model you can think of as just a distribution over responses given some prompt. And this response space is exponentially large, so you do not want to be enumerating over it. Luckily, we have some base model that lets us draw responses, draw decent responses that have some sort of structure to them. And we want to improve the base model. We improve the base model by some sort of iterative data collection and computation procedure, where we see some prompt, we sample some responses, we receive rewards for some responses, we do some computation, maybe we update our internal model parameters, and we repeat. And ultimately, our goal is to learn some pi hat, a new model, that maximizes KL regularized reward. So this is essentially, you want to maximize reward of your model, but you also do not want to stray too far from the base model. And this is captured by this KL regularization term. So in this work, we focus on a toy model, a toy version of this, where we assume that the rewards are linear in some known d-dimensional feature map phi. Under this assumption, you can show that the optimal policy is actually softmax linear. So it's proportional to the base model times exponential of the rewards. And this means there's an equivalence between learning this optimal policy pi star and estimating the reward function r star. And this is essentially how all the post-training algorithms proceed. Okay, so first let's look at classical passive exploration algorithms. One good example of this is iterative DPO. What this does is it alternates between data collection and model update. So in data collection, you just draw data from your current model. In the model update, you fit your collected reward data to a new model by fitting in the logits. And under our linearity assumption, this optimization step is actually just linear regression. So you can solve it via ordinary least squares in polynomial time in our toy model. Unfortunately, the number of these problems that you need to solve, the number of iterations you need to solve, is could be extremely large. It scales with the coverage of the base model. So this coverage parameter, C star, is the worst case density ratio between the optimal policy and your base model. It's essentially saying, how well does my base model cover the space of good responses? It could be good, it could be extremely bad. And because the number of iterations scales with this C star, the number of reward queries also scales with C star. So we might be drawing a huge number of samples, and we might be asking our humans or our verifiers for a huge number of reward queries. Active exploration methods have tried to mitigate this issue by introducing things such as optimism. So there's a recent work that modifies the DPO loss by adding an optimism term to the loss function. The statistical complexity is now much better. You can show that it scales polynomially in the dimension of the features and in the accuracy that you want. Unfortunately, the computational complexity now goes out the window. The optimization problem is non-convex even in the toy model. We don't know any non-trivial setting where this can be implemented in time better than exponential in the dimension. Okay, so can we do better? We show that we can. We show that there's an algorithm called spanner sampling. It learns a near optimal model. The number of reward queries is still poly D. And the runtime is now poly in D and in the coverage parameter C star. So compared to the passive exploration methods, we have essentially pushed the dependence on C star, the coverage of the base model, from sample complexity, from the reward queries, to just runtime. And compared to active exploration methods, we have avoided non-convex optimization entirely. And we have a guarantee that it gets better as the base model gets stronger. This is intuitively something that you really want. What is the intuition for this algorithm? The intuition is that if the base model has poor coverage of good responses, we do need to draw many responses from the base model in order to see the good rewards. But we do not necessarily need to query the rewards for all of these responses because we have some structure. What we can do is we can prune our responses to a small representative set, which we call a spanner, and then query the rewards just on this small set. And we use the feature map phi that we have to guide the pruning step. And that's the intuition. Okay, now there's a downside, obviously, of that algorithm, which is this dependence on coverage. We get this dependence in the runtime. You might ask, can we avoid this dependence? The first thing we show is no. Without further assumptions, any algorithm requires sampling at least C-star responses to learn a near-optimal model, and so this provides a lower bound on the runtime. And in the autoregressive setting, where the response space is a space of sequences, it's exponentially large, this coverage parameter could also be exponentially large. Can we do better with more assumptions? It turns out we can. We show that if you make an assumption about linearity of the regularized value functions for your base model and with respect to your rewards, we get an algorithm called multi-turn spanner sampling that learns a near-optimal model. It uses the same poly-D reward queries, and the runtime is now improved. Instead of scaling with the sequence level coverage, so how well do I generate a correct proof, it scales with action level coverage, like how often am I generating the correct token. And so this here is sort of fundamentally independent of Horizon instead of being exponential in Horizon, so it could be much better. Okay, the final thing I want to discuss is benefits of improper exploration. So almost all existing post-training algorithms use what you could call proper exploration. There's this very common framework where you have data collection and then you have updates. And the data collection is always you query rewards on data drawn from your current model in your model class. In our case, this model class is softmax linear models, so you're always exploring using softmax linear models. In contrast, spanner sampling explores improperly. It does not fit into that framework because it's querying rewards on responses that satisfy some sort of diversity condition with respect to the spanner, with respect to responses we've drawn previously. And you might ask, is this necessary for computational efficiency, or is there an algorithm that looks sort of more like the existing algorithms that achieves the same sort of guarantees? And perhaps that sort of algorithm might be more generalizable to more complex function classes. Unfortunately, we show that there's a lower bound here. So there is, under the randomized exponential time hypothesis, there is no proper exploration algorithm, namely one exploring with these softmax linear policies, that achieves simultaneously the poly-D reward complexity of spanner sampling and also the poly-D and poly-coverage time complexity of spanner sampling. So the takeaway is that efficient algorithms, that are both statistically and computationally efficient, may need either additional compute during this data collection phase to do the sort of diversity filtering that spanner sampling does, or we may need to be optimizing over different model classes. Maybe softmax linear model classes are not the right abstraction to be studying. To conclude, we show that a good base model is necessary computationally but not statistically for reinforcement learning, and that there are benefits of multi-turn RL techniques, where you assume some sort of structure about value functions, and there's also benefits for improper interventions for exploration. Some questions include approaches for exploration beyond the linear setting. This is maybe the biggest one, but the most open-ended, and also better model parameterizations than softmax linear that maybe let you get more like proper exploration algorithms. That's all I have. Thanks for listening.
Maybe I missed it, but can you give a sense of how these algorithms work and how implementable they are and whether you think they might work when the assumptions are not satisfied? I mean, maybe I missed this, but I couldn't get a sense of what the actual algorithms you're suggesting are.
Yeah, so the spanner sampling algorithm is sort of operating at it's operating at the sequence level. And it's two phases. There's like a spanner construction phase where you get some diverse responses according to your feature metric, your features. And then the second phase, you do some sort of essentially you do iterative DPO, but you've warm started with your spanner. So it's quite similar to iterative DPO, but it has this spanner thing. And the reason it's sort of restricted to the linear setting is because you need this feature map to tell you which directions you're like have more uncertainty in. So like essentially, if you can generalize your notion of uncertainty, then you would generalize like where you can apply this. But you could also just like apply this to like your last layer of features of your base model.
Yeah, nice work. So I have one question. So in pre-training, do you know how this so right now go-to approach for pre-training is MLE. So do you know like how this notion of coverage could be achieved during pre-training, which is also like more computationally expensive phase of the whole training?
I think that's a good question to ask Adam after the talk.
I guess in which case we have another time for another question.
Thanks, Rup. I guess I get a shot. Is there any hope at all to sort of, even under some like additional assumptions, to understand the robustness to imprecise rewards for any of these settings? Like presumably the spanner type of thing like might actually, by querying less points somehow, might be more susceptible to imperfections in the reward.
Yeah, I guess there's all these works about like RL where you have like approximate linearity, and I think you often like I cannot be certain that the setting tracks, but like you often face these blops of like square root dimension or linear in dimension. A lot of these seem inherent to me, as far as we know.
All right, let's take the rest of the questions offline and thank the speaker again.
Yeah, this one? Yeah, perfect.
Well, our next speaker is Chirag Paparaju, and he's going to talk about proofs as explanations, short certificates for reliable predictions.
Okay, thanks for coming, everyone. I'll be presenting some recent work on certifying predictions. This is joint work with Avram Blum and Donia Salas at TTIC and Steve Haneke from Purdue. Okay, so I guess it's can't understate the essence of having explainability for predictions as machine learning systems are more widely used in critical applications like medicine. So here we have a patient who's sad, and the doctor is recommending that the patient should undergo surgery for their ailment, and this recommendation is being given to the patient because some robot is telling the doctor that he should undergo surgery. And the patient is a little uncertain about this prediction, and what might make the patient a little more trusty of the prediction is that if the prediction is accompanied by some sort of evidence like this. Like, let's say that there's some the robot looked at some training data before coming up with this prediction, and then the robot says that I suggest surgery because in my data set, I saw that patient X who underwent surgery for the same ailment benefited, and patient Y also who suffered from the same ailment benefited. And then there's the whole list that the robot could enumerate. And this might inspire some confidence in the patient here. Okay, so that's kind of where we started from. We were looking for evidence in the training data that might support a prediction. And to formalize this kind of notion, let's say that there is some training data set that, this is a binary prediction task, there's some training data set that your model is learning on. We are assuming that this data set is labeled by some hypotheses in a known hypothesis class. And yeah, we wish to certify some prediction that we are making on a test point X. Let's say that we are predicting a positive label on a test point X, and we want to certify this prediction. This is kind of the only definition that our whole work revolves around. It is that of an agreement region. So what is an agreement region? We'll say that some test point X together with the label plus is in the agreement region of a training data set S with respect to a hypothesis class H. If every hypothesis in the hypothesis class, which is consistent with the training data set, if it labels the test point as positive. So every hypothesis in the class, if it attains this labeling on the training data set, it must label the test point as positive. And that's when we'll say that this point is in the agreement region. and then any subset of the training data set which satisfies this property that the test point is in the agreement region of the subset will serve as a certificate for this point. Okay, so with that definition, we can ask, if I have a test point that is in the agreement region of the training data set, what is the smallest certificate for this test point that I can extract from my training data set? And that is the question that was the motivating question in our work. So in a picture, we have this training data set, and the agreement region of this training data set is some superset of it. We can hope to certify any point in this agreement region, but what we are looking for is some small subset of the training data set, which can also serve as a certificate for the test point, because the test point also belongs to the agreement region of this subset. So this is what we are hunting for. So let's start with, I guess, a simple example. Let's assume that we're operating with half spaces in D dimensions, and this is some training data set we have, some positive points, some negative points. To pin down what the agreement region of this training data is, we can find the bare minimum hypothesis that labels these points as positive, that's this hypothesis. We can find the bare minimum hypothesis that labels those points as negative, that's that hypothesis. And we can be sure that everything in this kind of shaded region here is in the positive agreement region of the training data. Any hypothesis that labels these points positive, those points negative, must label every point in this region as positive as well. You can observe that actually this region is the cone of the region that's determined by negating the negative points. So that's what basically I'm going to say in these sentences over there. I'm saying that if I flip the negative data points and I look at the cone that is determined by this multi-set of points, that is precisely the agreement region of this training data set. And now I have this nice theorem by Caret-Theodori, which says that any point in the cone determined by a data set is actually in the cone of a subset of the data set, which is only of size the dimension of the data set. So this already gives me that I can figure out a certificate of size at most the dimension of the underlying space from this data set. And once we see the dimension and we recall that we're working with linear hypotheses, we can start kind of smelling the VC dimension. It always shows up everywhere in learning theory, so we might ask, maybe the VC dimension is the right number for characterizing the size of the certificate that I can extract. But then we think about another example, which is that of singletons. So what is the class of singletons? You have n points. A singleton is defined with respect to a domain of size n. The class of singletons is basically the indicator functions on this domain. So there are n functions, all the n indicators. This class has VC dimension 1, so that's a constant. And let's suppose that our training data set comprises of the first n-1 points labeled by the last hypotheses. So if this is our training data set, we know that the last point, its label is pinned down. It must be realized by some hypothesis in the class. I'm seeing that everything is labeled 0, and I'm being asked the label of the last point that must be positive. So the last point is in the agreement region of this data set. But you can also observe that any proper subset of this data set does not render the last point to be in the agreement region, because we don't know if it's going to be the indicator of the point that we missed out. So in this particular case, you cannot hope to get a certificate of size smaller than n-1. In particular, you can't hope to get a certificate always of size VC dimension. Okay. But this kind of singleton's example is what essentially characterizes a combinatorial quantity known as the hollow star number. And we find out, so let me tell you what the hollow star number is. The hollow star number is basically a generalization of the singleton's thing that I described. So it's a definition with respect to a sequence of endpoints and a labeling assigned to these endpoints. We should have the property that the labeling is not realizable by any function in the hypothesis class. But if I remove any point from my sequence, that should be realizable by the hypothesis class. So coming back to my singleton's example, you can take all the endpoints and you can assign a labeling of 0 to everything. Because I only have indicators, this is not realizable by the hypothesis class. But the moment I kick out any point from here, that becomes realizable because the indicator on that point realizes this. So This is a hollow star. The size of the largest such set is the hollow star number. And that's precisely our first result. We say that, we show that the smallest certificate that can be extracted from a training data set for a point that's in the agreement region is precisely characterized by the hollow star number. So you can always find a certificate of size, at most the hollow star number. There are instances where you cannot extract certificates that are smaller. The singletons one is one of those. And throughout this work, we also operate with corruptions that might exist in the training data. So we have a notion of a robust certificate. It's the natural definition, and we establish all these results in the robust case too. I just wanted to mention that. Okay, so that was the worst case. Those were the worst case results. We also consider a more natural setting, which is more in line with pack learning theory, where we have a test point, but all the training data is drawn IID from some distribution. And we want to ask, if a training data is being drawn from the distribution, when can I start extracting a certificate from the training data for this test point? So for that, we must first ask, when does the test point even fall into the agreement region of the training data? So that's the question that we ask. Like, so if I have a test point with a positive label, how many points do I need to see so that this point lies in the agreement region? So in this particular case, let's say that the distribution is just supported on these 3 points of the triangle, and the test point is the center point. And let's say that the hypothesis class we're considering is just linear separators, and the linear separator is outside the triangle. So it's labeling everything positively. So in order to certify the center of the triangle with a positive label, I must see, I'm done. Okay. So I must basically see all the points on the vertices. So this question is asking, how many points do I need to see so that I see all, how many points do I need to see so that I see all the points on the vertices? So anyway, I'm running out of time, but I'm going to tell you that we define a notion of a certificate coefficient for every test point, and we determine a sample complexity for rendering any test point that you care about to be in the agreement region of the training data set. This is where the VC dimension does show up. So it does show up finally at some stage. So in our analysis, we show that this is the optimal sample size one needs to draw to render any test point into the agreement region of the data. Okay. I think I'm going to just go to my conclusion slide. Okay. So, okay, we defined this notion of certificates. We characterized what the worst case certificate size should be for every test point. We characterized distribution-dependent certificate sizes for test points. There are nice open questions here in terms of, okay, so we show what the size of these certificates should be, but we don't really give algorithms to construct these certificates. So that's an interesting open question about how one algorithmically extracts these certificates from the training data. And yeah, maybe I'll just mention that even for linear classifiers, if we know that a point is in the convex hull of some points, finding the smallest subset for which that point is in the convex hull is in general an NP-hard problem. But for other cases, maybe we have efficient algorithms. So that's an open question. Yeah, thank you.
We have time for maybe one question. To the speaker.
Over here. Thanks. Great talk. What if the definition of a certificate required only, like, I don't know, a large fraction, strictly less than 1 of agreement? Then does your setting cover that?
So that is under this robust version that I mentioned. So when I say, we also considered the robust version, it allows for, you have a budget B. Let's say I allow for B mislabelings on the training data set. If all the hypotheses that make at most B mistakes on the training data agree on the labeling on the test point, that's the notion of a B robust certificate, and we characterize that also.
All right, let's thank Chirag again. He's also going to give the next talk on exploring facets of language generation in the limit.
Thanks for bearing with me. And this is a joint work with my advisor, Moses Charikar. Jason, I think, did a lot of the setup, so I'm going to like draw on that and not do setup. But so let me skip on all of this. Okay, so this is the framework of language generation in the limit that was recently introduced by John Kleinberg and Sendhil Munellathan. It's been receiving quite a bit of attention. So let me just go over the setup. There's some collection of languages that we know. It's a countable collection. And the adversary comes along and chooses some language from this collection and starts giving you strings one at a time in an online fashion. At every time step, the algorithm can generate a string. And we'll say that the algorithm generates in the limit if beyond some finite time, t star, the t star, which all the strings that the algorithm generates are from this hidden language that the adversary chose, and they're new. So this is the game. Beyond some finite time step t star, we want that every string that the algorithm generates is new and in the language. So notice here that t star there, it can depend on both the target language that the adversary chose as well as the particular enumeration that the adversary is doing. We might not be too happy about the dependence on the enumeration because there might be pathological enumerations of the adversary which may delay the time at which the algorithm generates for as long as the adversary wishes. So this was formalized in the work of Lee, Raman, and Tiwari via the definition of non-uniform generation in the limit. So the setting is the same. There's a collection, adversary chooses a language, starts giving it to you. But you'll say that you satisfy the stronger property of non-uniform generation in the limit if the moment the algorithm sees some t star many strings, where t star only depends on the language that the adversary chose and not the enumeration order, the strings generated are correct and are new. So going back to my picture, there was this, so the adversary chose some language. At t star, beyond t star, I was always correct. But now if the adversary changes the strings that he's showing to me, I should still have the property that at beyond t star, I'm still satisfying the correctness property. And this should hold regardless of the t star strings that I see. So that's the definition of non-uniform generation in the limit. It's a stronger success criterion. And the open question that Lee, Raman, and Tiwari posed in their original paper was, can we non-uniformly generate in the limit from every countable collection? So this was a result that Kleinberg and Munellathan showed. They showed that the spectrum of all countable language collections is generatable in the limit. And because this is a stronger definition, maybe you can only satisfy it for a subset. But we showed, and they also showed concurrently, that you can actually non-uniformly generate in the limit for the entire spectrum. So you can achieve this stronger property for essentially every countable collection. So that was the first result. But maybe something which was brought up was, what is the kind of computational resources that one assumes when doing these kinds of results, right? So let me tell you first about what our non-uniform generation algorithm requires to achieve this guarantee. So it requires access to an oracle to which I can issue the following kinds of questions. So I can tell the oracle to tell me if the intersection of some finite subcollection of languages is finite or not. So I can ask the oracle, can you please tell me, is the intersection of L1, L2, and L5 finite? These are the kinds of queries that this algorithm requires for it to achieve this non-uniform generation guarantee. Whereas the original generation in the limit guarantee of Kleinberg and Munellathan only required access to membership queries. So what are membership queries? The algorithm can choose any language of its choice, and it can choose any string that it likes, and it can ask the oracle, does this string belong to this language? Note that it can't just ask whether a string belongs to the target language, because the algorithm doesn't know what the target language is. It can only ask membership in a language of its choice, which is not the target language. It might be, but it doesn't know. So you can ask, like, okay, you can satisfy this stronger non-uniform generation guarantee, but can you also do it with these kinds of queries? So the second result which we showed was you can do non-uniform language generation for every countable collection, but you provably require stronger oracles. In particular, we show that even if you want to non-uniformly generate in the limit for all collections of size 2, you can't do it only with membership queries. Like, we show that you can do it with the subset query oracle, but definitely you can't do it with only membership queries. So hopefully I'll try to give you a sense of this proof at the end. But yeah, so that's the punchline. You require stronger oracles to do this task. Okay. So what is another kind of feature of Kleinberg and Muller-Nathan's original algorithm? It suffers this problem which they call the validity breadth trade-off. So, okay, so how does this algorithm start? Okay, so there's this there's this language that we care about. And the algorithm initially starts producing all junky strings at the start. So it doesn't know what it's producing. For some time, it'll just produce strings outside the target language. Then it steadily refines all its nonsense utterances and starts only generating from inside the language. So that's when T star has kicked in and it's generating validly in the limit. But a curious property is that beyond this time, as time progresses, the algorithm only produces new strings from subsets that become smaller and smaller. So these are all valid strings, but they are only from these increasingly smaller subsets of the language. Kleinberg and Muller-Nathan make a nice comment in their paper that this kind of resembles the way humans acquire language, in that when we are kids, we start off speaking like gibberish, but then we pick the language, but then as we grow old, we have some inertia, so we don't always keep updating ourselves with the new lingo that's in town. But this is kind of a nice picture of this is reflected in their algorithm too. And they ask, is this kind of validity breadth trade-off fundamental to language generation in the limit, or can we somehow get best of both worlds, also generate validly, but also cover everything from the target language? And informally, this is the theorem that we show. We show that there is a collection for which, if you have to generate validly in the limit, in the sense that you don't make any hallucinations in the limit, then you provably must have to miss out an infinite number of strings from the target language. So any algorithm that achieves breadth in the language must have infinite hallucinations. So I guess one nice way I like to think about this is, at least this language generation in the limit framework is proving to be a nice sandbox for grounding practical phenomena that we see in LLMs. So this is one nice feature. And I should say that subsequent work by Kalavasis, Mehrotra, and Velekas also precisely characterize the kinds of language collections for which we can achieve various notions of breadth. So this is now quite nicely pinned down. And we also kind of study a different model where the algorithm now is allowed to ask questions about membership in the target language itself. So note that even without these kinds of questions, you can always generate in the limit. So these kinds of questions for every countable collection. So these kinds of questions can only, we should ask stronger guarantees if we are allowed these kinds of questions. And we show that for the notion of uniform generation that Jason mentioned, we precisely characterize what collections can be generatable in the limit with feedback. So that's another contribution in our work. But let me just quickly summarize what we've shown in our work. We showed that every countable collection can be non-uniformly generated. We showed that to do non-uniform generation, you need stronger oracles. You need something that is stronger than membership queries. We propose a definition for generating with breadth, and we show that there are simple collections for which you cannot provably generate the entirety of the language. We further characterize the language collections for which you can successfully do this task of generation with breadth. And then we also characterize uniform generation with feedback. And going forward, I think we still don't have like a nice specification of what agnostic generation in the limit means. So I think there are some noise models for generation that have been considered recently, but I think a broader definition of what agnostic generation is still lacking. So that's the summary, but okay, we did a tutorial on this stuff earlier in court, and I think a more detailed version of everything that I presented is available there. It's available at this website too, and we'll try to keep updating it with content, but that's all I have.
questions for Chug? If not, let's thank him again. There's one question I didn't see.
Yeah. Do you have any interesting examples where this thing can be implemented computationally efficiently? For example, if I take all regular languages, then would you be able to implement this or something like that? I don't know.
Right. So this notion of membership queries, I think if you're given a description of the like say the finite automata that generates if there's like an enumeration of all the finite automata in the world, and then there's a description, you have access to these finite automata, then you can implement the algorithm using a finite number of queries to the collection of finite automata that you're given to. So it's still like very much dependent on the enumeration order and the language that the adversary chose, but I think the short answer is no, it's not practically implemented.
Thank you.
All right. Let's thank the speaker again. Well, our next speaker is Guy Kornowski. He's going to talk about trade-offs in data memorization. We are strong data processing inequalities.
Hi, so thanks. This is joint work with Vitali and with Shin from last summer, where Shin and I were interning at Apple. So this talk is about data memorization, which is the empirical phenomenon in which it seems that large models memorize a lot about their data set. And this was exemplified in the relatively early age of large language models with early versions of GPT, that certain prompts can make it just basically spit out personal information from people that appears on the web. And more sophisticated models required more sophisticated attacks, but it's still the case. And one may think that this is just an artifact of how people train LLMs via next token prediction, but it seems to extend way beyond that. For example, also in the context of, this third work was in the context of image generation, in particular diffusion models. So it's by now pretty well established empirically that data memorization happens across the board throughout different domains, models, and algorithms. And this obviously raises some societal concerns, both in terms of privacy and copyright issues. But moreover, for the purpose of this talk, it also raises learning theoretic questions. I mean, in terms of why and when does this happen? And can we make sense of it in the sense that can we quantify memorization somehow? Okay. So in order to formalize what we're talking about, we need to formalize what access memorization is. So we follow this pretty compelling framework introduced by Brown et al. A couple of years ago. So statistical learning, we gather n samples IID from some unknown distribution, and we process it using some algorithm to get some model or hypothesis. And what we assume is that there is this implicit parameter theta, which is actually what we're trying to learn. So one can think of as a simple example as trying to do clustering, and theta is just the description of the means of the clusters. Okay? So if we knew theta, we solve the problem. And theta is actually what we're trying to do, recover it. And we even assume that before we actually get to see the samples, there was some data generation process in which theta was sampled according to some known prior. We might know the prior, but we don't know the instantiation of theta. So this is kind of our prior knowledge of the world. Okay. And then we can define access memorization as the conditional mutual information between the model that the algorithm outputted and the sample that it saw, conditioned on the true parameter theta. So one way to interpret this quantity, quite naturally, is it's the conditional mutual information, it's the mutual information, between the model and the data set, which contains also important information that we actually want to learn after we factor out all the useful information about theta. So what we're left with is this non-negative quantity, which roughly measures the amount of bits that the model contains about the data set, which are uniquely about the data set. And kind of a known view established by a long series of works dating to at least as old as Blummer et al. Of Occam's razors learning is that if you don't memorize a lot, then you generalize. And in this work, we kind of take a complementary view and show that in certain cases, you need to memorize a lot in order to generalize. So in particular, we study a variety of d-dimensional cluster identification problems. So by cluster identification, what I mean is that we're doing binary classification with respect to one fixed known cluster, say like just an isotropic Gaussian, okay, around 0, and some unknown cluster around theta. So our goal is essentially to kind of learn the unknown cluster. And what we show is that for a variety of such tasks, on one hand, if the clusters are sufficiently separated, statistically it's easy. We can do it with very few samples. But in terms of the memorization, any good algorithm, so if we look at any algorithm that actually solves the task better than a random guess, then what we see is that the memorization behaves like the dimension over some constant, which is distribution dependent. And that constant grows with n, meaning that the memorization decays with n. And note that this is typed as the infimum over all good algorithms, meaning that on the lower bound end, it means that the only way to learn is to memorize this amount of bits. On the upper bound side, this means that with more and more samples, there are low memorization learners. Okay? So kind of the take-home message is that more data is both necessary and sufficient in order to reduce memorization. And I want to stress out that this is kind of completely orthogonal to generalization. So generalization is possible even with very few samples, but in order to generalize without remembering the specific pieces of information about the data set, you need more samples. Okay? So in particular, some of the applications we consider are natural clustering distributions. So one can consider a Gaussian cluster or a Boolean cluster or a sparse Boolean conjunction. It's not very important to remember what these specific distributions are, but the point that I want to make is that we can characterize in all cases the memorization decay rate, that constant that depends on the distribution and on n, and it's very different in all cases. So we get this kind of diverse profile of how memorization and the sample size trade off one another. So it can be either pretty smoothly in the case of Gaussians, or way faster in the case of sparse Boolean conjunctions, and somewhere in between in the Boolean case. Okay, so moving on from this kind of simplified one cluster model towards modeling real-world distributions, which is, I guess, what people in this room are interested in the context of language models, which is what this session is about. So recall that LLMs are simply multi-class classifiers, and how they do it is next token prediction. And what they're implicitly trained to do is to compute some semantic data embedding. And in this embedding space, it's hypothesized that hypothesized and kind of empirically validated that data distributions behaves like a mixture of clusters, so that nearby points in the same cluster likely have the same label. Okay? And moreover, there's a lot of evidence that natural distributions, the sizes of the clusters are very, very heavy-tailed. And this makes sense. I mean, if you think of natural distributions over words or images, it's kind of clear that there are many things that you'll see quite rarely, but you need to learn a lot of things like spoon and rope and locker and whatnot in order to actually understand natural language. So in this context of like a heavy-tailed multi-cluster classification, previous works by Vitali showed first that you need to memorize the labels of clusters, and then the more advanced work that I alluded to earlier showed that you need to memorize singleton clusters, meaning that all the clusters which have only a single representative in the data set. And our techniques allow extending way beyond that to kind of have a complete view of the necessity of memorizing all clusters in a way that the total memorization that the model needs to have about the data set scales like the sum of over all clusters of how much you need to memorize per cluster. And inside any cluster, the amount of memorization scales like our results show, like the dimension over some distribution-dependent constant, that depends on the number of points you see relevant from that cluster. Okay, so this gives kind of a complete view of how, at least in this theoretical model, memorization behaves. In the time I have left, I want to, it's even in the title of the paper, Strong Data Processing Inequalities, so tell you what this is, because I think this is a really cool tool that we apply here. So recall that the data processing inequality simply states that for any Markov chain, x leads to y leads to z, it holds that the amount of information that z holds about x cannot be larger than the information it has about y. And this is clear because all z sees about x is factored through y. So a strong data processing inequality talks about the case in which y is kind of a noisy, lossy version of x. So a joint random variable xy satisfy rho SDPI for some constant rho which is strictly smaller than 1 if for every way in which I post-process y, the amount of information I have about x, which I started with originally, is strictly smaller than the amount of information I have about y, because I lost some of the information in the channel between x and y. Okay, so this is just a definition, and this is very well studied in information theory, and kind of canonical examples are correlated Gaussians or Bernoullis satisfy this definition, depending on the correlation between them. So why is this useful in our context of memorization? Recall that implicitly in our data model, we have two Markov chains. One is the Markov chain leading from the unknown parameter theta to the generation of the samples. But there's another one, which is, at the end of the day, we want to be able to predict fresh test samples, right, according to the same distribution. And we know that in order to classify some fresh sample from the distribution, if we are doing anything good in terms of prediction, it must be that the model knows something, has some bit of information about the test data, right? And if it's the case that the test and train data with respect to one another satisfy this SDPI condition, we automatically get that the amount of information that the model has about the data set must be 1 over rho times larger, okay? But this counts useful and unuseful information alike. So if we further assume that there's also like noise in the way we get to see the samples in the first place, meaning that there's some SDPI between theta and the samples representing the distribution dependent on theta, then we know that what the model encodes about theta, about S, the sample, only a fraction of that is actually relevant. So overall, concluding these two, we kind of automatically get that under these two SDPI conditions, the excess memorization of the algorithm must scale like this mathematical term here. And what we do to prove our lower bounds that I presented earlier is actually just computing these constants, which is very non-trivial. And in the paper, we show kind of general techniques how to compute them, which I won't have time to get into. And in terms of upper bounds, we just need to match it with concrete algorithms, which is what we do. So to conclude, I think our theory provides a relatively plausible explanation of this widespread phenomena of data memorization seen in practice. And I think a kind of non-trivial fact is that it's statistical rather than algorithm specific. Nowhere did we discuss the specific ways that algorithms actually learn. It's kind of inevitable under certain distributional assumptions. And it shows that sometimes memorizing unimportant information can be important, specifically in cases in which you don't have a lot of relevant data from some cluster and you don't know what information is going to be important. And as I said, we have a bunch of technical information theoretic tools, which I find pretty cool in the paper. So if you're interested in those kind of stuff, you're welcome to check it out. And yeah, thanks.
Thanks. So I want to ask about that point about the algorithm specific. So if I understand correctly, you get a lower bound for every algorithm, and then you saw there exists an algorithm.
Right.
Do you know if the natural algorithm, if you just do ERM or just gradient, do they achieve this, or are they more leaky?
Yeah, so it depends on which ERM. So the algorithms that we design for our upper bounds they're kind of a non-trivial ERM. So for example, you can think in the Gaussian case of just trying to classify two Gaussian distributions. the natural thing is, you saw samples from p theta and you're trying to estimate theta, just take the mean. So, but that still memorizes relatively quite a bit about the sample, although it does still decay with the sample size. But if you really want to squeeze that down to what you can do, is you need to project that. So then, like, kind of so semi-natural in a way.
Does that suggest what's the realistic settings?
I mean, realistic setting is a very broad term, so I'm not sure what to say about that.
Any more questions? If not, let's thank the speaker again. Our next speaker is Themis, and he's going to talk about compression barriers in autoregressive transformers. And that's the last talk of this session.
Thanks for sticking around to the end. Themis, I'm from Boston University, and I'll talk about compression barriers for autoregressive transformers. Mainly the main question we set out to address is whether token generation in transformers is space efficient or can be made space efficient. This is joint work with my advisor, Christoph Onak at BU, and in a nutshell, as many talks have already touched on, LLMs these days are mostly autoregressive. This tends to change a little bit, but essentially next token prediction is the main way we kind of generate language. And that kind of allows us to view inference as a streaming problem, which gives us access to a lot of nice streaming algorithms and sketching algorithm techniques. And also, transformers, the most popular model these days, are mostly based on attention. And this attention mechanism is, I'll touch on how exactly it works in a bit, but essentially, the main thing to remember for now, and you probably know it, it's very computationally inefficient, both in terms of time and space. So in a nutshell, our contributions are hardness results on the space complexity of autoregressive token generations with transformers, and a few algorithmic insights about what you can do to mitigate this hardness under specific structural assumptions. So let me introduce the problem. Suppose we want to generate a sequence of n tokens in a transformer autoregressively by predicting the next token. Transformer models typically do this by generating 3 types of embeddings in a d-dimensional space for every token that they generate. These are called the query, key, and value vectors. And so what typically a typical transformer does is it stores the key and value embeddings in a cache called the KV cache, and then uses all of those embeddings in a certain way that I'll talk about in a second via the attention mechanism to kind of produce the next token. So the way it does that, the way the attention function works, I've written it down here in a way that's slightly different from the way it's typically defined. But basically, you can think of it as selecting a value vector v out of the n ones you've seen so far, according to some distribution j. So you pick an index, and then you spit out the jth value vector. And the distribution that you pick the index j with is a categorical distribution d that depends on the ith query vector and every other key vector you've seen so far. So you look at all the inner products between the latest query vector and all the other key vectors, and you softmax them. You get a categorical distribution, use that to pick index j, and then take an expected value over your value vectors. That's what attention does in a nutshell. And the reason why I'm giving this definition instead of just a long blurb of algebra that you typically see is because it lends itself naturally to sampling approaches. So this KV cache, if we choose to store all the value in key vectors every time, can grow quite a lot. And when you do inference with a typical LLM, typically it can grow to more than 50% of all the memory you need. And that's bad. It takes up more space than the actual model parameters in a typical LLM.
So the gold standard would be to achieve sublinear space utilization at inference time. Lots of algorithms and lots of work in the last 2-3 years have tried to do this, and most of those works make a lot of empirical observations about the structure of the input embeddings, and as a result, they manage to shave some space. For example, lots of works are based on clusterability, some modularity, some of them bound the norms of the embeddings. And our question was kind of, okay, what is the minimal surface of structure you need on these input embeddings that will allow you for sublinear space token generation? Okay, the result that we give is a bit of bad news. You cannot do this in the worst case, even approximately without sublinear space. So if your input dimension d is like log n or more, you need the full n times d space. If you are sublogarithmic, then you can get slightly better, d times e to the d, but still pretty bad. The proof, if you've seen space lower bounds in streaming or sketching, is not very unnatural. It follows through a communication complexity lower bound. The problem we use is this index problem. Alice has a string and Bob has an index, and Alice sends one message and one message only to Bob, with which Bob is supposed to predict the jth bit of Alice. And so we managed to encode an instance of this problem using the attention mechanism. Alice encodes the string x using the value matrix, and then uses the key embeddings in an approximately orthogonal manner. This can be done using a JL transform plus probabilistic method argument. And then Bob uses his index to kind of input the query embedding appropriately. So in picture, the proof looks kind of like this. Alice builds this K matrix of approximately orthogonal vectors, and Bob inputs this query embedding to kind of lead the softmax to spike at the desired index. For low-dimensional embeddings, like little o of log n, the picture is slightly better. There's an algorithm by Zandiehan, Mirokni, and Karbasi proposed like last year that achieves sublinear space, even though it was not stated as such. And it assumes that you can cluster the key embeddings. So that's not always the case, but if it is, what you can do is you can store representatives of each cluster and sample, so you can reduce memory. It's pretty a natural and very neat approach. It looks kind of like this. You have a bunch of clusters, you store representatives, and you just sample from those clusters to reduce memory. So, but it doesn't really work if the inputs are not well clusterable. However, if the dimension is little o of log n, they're always clusterable. And this is just a simple covering number argument. You could just look at the L2 ball around the origin and kind of like show that if your dimension is really small, there's not enough points to fit. Okay, a few things. Sparsity is one thing people have been using a lot to save space. So can sparsity save us? Not really, if it's unstructured. So we need to know something, we need to assume something about the sparsity pattern of the matrices involved. For example, one thing that we look at is the sliding window strategy. We extend it a little bit so that the tokens outside of the sliding window are still in the support of the softmax instead of just zeroed out. And in this case, you can do a reservoir sampling approach, pretty typical in streaming, to get sublinear space. Finally, we give a non-adaptive lower bound for time complexity. Non-adaptive algorithms are ones that pre-decide the data access pattern before seeing the actual stream. Yao's minimax principle is a pretty common technique in this kind of lower bound. You can show that in the worst case, you need linear time. But if you are, and why is that important? Because a lot of algorithms that are hardware efficient actually do like to be non-adaptive. But if you are allowed to be just a little bit adaptive, you can do stuff like k nearest neighbors, top k, for example. You can look at the top k tokens and achieve sublinear time. Yeah, that's pretty much it. Future directions here. If you're not autoregressive, then what can you do? And what kind of structure do language embeddings have that allows us to save space? Thank you.
Thank you.
Thanks. Sorry, could you just say, is the clusterability, when you say that the tokens are clusterable, is that exactly the same as like being a net on the ball, or is there some other definition for
I
what
think
this
it's very
clusterability-
similar to that. Yeah, that's right.
Thanks.
In your paper, do you investigate the structures of like sparse attention matrices?
As in, like specific type of structural patterns.
Yeah.
The only one we look at is sliding window. It is worth to note that a lot of empirical work has shown that if you have low rank, then you can be much more efficient. Or a lot of, for some reason, a lot of real language matrices actually have the first couple of tokens be really, really relevant and the rest of them not. Beyond that, we only looked at the sparsity, the sliding window. Yeah.
All right, any more questions?
Wait, sorry, just to follow up on the last Audrey's question. In the low rank setting, sorry, maybe I missed it in the talk, but what is the space requirement if you assume this low rank?
Oh, yeah, I didn't really talk about that specific setting. Yeah, I forget the exact bound, but there's one of those papers that tries to exploit the low rank structure. I just can't remember it. Yeah.
All right, this concludes the session. Let's thank Tamis and all the other speakers again.
Ah, wow, wow.